அனுப்பிட்டாங்களா? ம்.
That is a long short-term memory network as well as a gated recurrent unit or known as JRU. So before starting this presentation, this is my plan of talk. Basically, I'll talk about the basics about what is called RNN, LSTM, and why this LSTM is important compared to this RNN, and how this GRU overcomes the limitations of this RNN as well as the LSTM. So if we look into our history of deep learning, basically these deep learning models are mainly classified into convolutional neural network, which is popularly known as the CNNs or convnets. So in case of this convolutional neural network, these are known as the feed-forward networks, in which the output we can get by forwarding the information or passing the information from the input to the output. So there is no feedback. That means we can say there is a not depending upon the past input or the past states. So recurrent neural networks are such kind of networks in which we are depending upon the past state, and how it is very essential in case of estimating or predicting certain output in case of medical field or in case of speech recognition or any kind of language recognitions that we're going to discuss. So there is another kind of network is known as stack autoencoder, which works on the principle of encoding and decoding process, in which the total images are basically converted into a latent space, and from the latent space we are backing up or back into to the original or any other smaller dimension of the images, which is particularly used for dimensionality reduction or any kind of segmentation, feature extraction, etc. And deep Boltzmann machines basically used for classification purposes, and the reinforcement learning are real-time applications people are using, which basically depends upon the condition of the environment by taking some feedback and maximizing the rewards. So as we are talking about the recurrent neural network, in this topic or in this recurrent neural network, basically we look into what to learn, basically what this recurrent neural network is learning, and what is RNN, and how this RNN basically remember the previous inputs as well as the past states to predict the future output, and how does this recurrent neural network is differ from this deep neural network, and how exactly it helps in case of predicting the outputs, the back propagation through time, and how this back propagation helps in training the recurrent neural network models. And here we'll talk about one of the two important problems in case of recurrent neural network. One is called vanishing gradient problem as well as exploding gradient problem, and the types of the recurrent neural networks. Here is the best example, that is the sun rises in the dash. So here I have given the statement, the sun rises in the dash. If I will ask this question to everyone, then you can better answer that the sun rises in the east. How we can able to identify that this blank which is present at here, that to be east. Basically this depends upon the
Yeah.
Participants, I think Sir is facing a technical difficulty. He'll join within 5 minutes. Sir, sir, we have made you as co-host. Can you now unmute, sir? Sir, are you able to unmute?
Even sir?
Sir, we can see a screen
Yeah,
also.
yeah. Sorry for the
Thank you, sir.
inconvenience.
No problem, sir.
No problem.
So as we are talking about the recurrent neural network and uh, line, that is the sun rises in the dash. So in this case, in order to fill the blank space, so we have to know what are the previous words are. Basically, the sun rises in the east. So in this case, we are predicting this by the help of the previous information that is present in this line. We are reading.
Sir,
everyone? Am I audible?
Yes, sir, you're
Yeah.
audible, sir, but your screen is not visible.
Okay. Yes, it's visible now.
Yes, sir.
Yeah. So this feed-forward network cannot predict the appropriate word. That is nothing but the east. So the reason behind is that each input is independent of the other input. That means as we are talking or we are saying the word the sun rises in this. So this the first word that is the second word the sun, the third word that is rises, the fourth word in, and the fifth word the. So these are independent of each other. We are not identifying what is the context present inside this line by the help of a feed forward network. So the prediction is only based on the current input in case of feed forward network. But whereas in case of recurrent neural network, it understand the context that is present inside this line. So in case of feed forward network, it doesn't or don't remember any previous input. The word alone preceding the blank, or that is the this blank line, is nothing but the e. So based on this e, the we cannot able to predict what will be the next word, that is the east. So in case of feed forward network, which is moving or giving or providing the output based on the inputs which is moved in a forward direction, we cannot able to what will be the next word. So in case of recurrent neural network, we can able to predict it. So that is the difference between the recurrent neural network as well as the feed forward neural network. So now the how we can able to give a solution to this. As we are talking about the sun rises in the dash. So this recurrent neural network can be used to identify or the predict this blank line or the space. So because the predict the output based on the current input as well as the previous hidden state, not the previous one. So recurrent neural network works on the principle of the hidden state. So what exactly the hidden state and how exactly the hidden state can able to predict this word, that we are going to discuss in the future slides. So now in case of feed forward network, this works on the previous word only. So as it works on the previous word, the only, so the east cannot be predicted in case of the feed forward networks. So, but in case of this recurrent neural network, it works on the principle of the hidden state information as well as the context informations. So we can say that it captures some contextual information and it acts like a memory and identify the context of the sentence. So as we are talking about the sun rises in the dash, so in this case, we are able to identify what is the contextual information present in this line. And this recurrent neural networks behaves like a memory such that it can able to identify what information are present in the previous words such that this word can be the best fit to this line, and it identify the context of the sentence. That's what already we are discussing about. So now we are talking about the recurrent neural network. So how this recurrent neural network basically works and how what are different layers that basically it consists of. So basically, if you look into the structure or architecture of this recurrent neural network, it has an input layer, it has a hidden layer as well as the output layer. And this hidden layer is nothing but multiple hidden states corresponding to the word or corresponding to the alphabet or the or different type of symbols. So now how exactly basically this is working? So if you look into the architecture, basically here I am uttering the word, the sun rises in the dash. So in this case, the will give rise to the first hidden state. The sun gives rise to the second hidden state. Rises given to the third hidden state. In given to the fourth, that is hidden state, and the given to the hidden state, that is the this hidden state, and the output of this hidden state is nothing but the east. So we can say this or we can discuss this in a much better way, that in the first pass we are passing the input that is d, in the second pass we are passing sun, the next pass we are passing rises, in the next pass we are passing in, and next the, and the output is the east. So exactly what is happening in this case? In this case, we can summarize this information by the help that every time passes the input word as well as the previous hidden state. So in this case, the input word is passed into the model as well as the previous hidden state. We'll just look into this exactly how it is happening. So suppose I will take the first word, that is the. So in this case, the is passed into the model, that is the hidden state H0. And what is the initial hidden information, that is called your hidden state information, that is passed into this model. Suppose I will consider this state, that is nothing but the hidden state H1. In this case, what is the input given to this state? The input that is given to the state is nothing but the sun. And what is the information, or that is model information passed into this? The hidden state information that is passed into this state is nothing but H0. So similarly, if we'll consider the hidden state that is equal to H4, the information that is passed into this hidden state, that is nothing but the. And what is the hidden state information? The hidden state information that is passed into this, that is known as the H3. So from this, we understood that every time the model passes the input word and the previous hidden state information. So as it consists of two information, that is one is the hidden word and another is the previous hidden state information, it can able to predict what will be the next word of the sentence, or the what will be the blank word for this sentence. The sun rises in the dash. So in the dash, it will be the east. So we can say that the final state output is nothing but the blank word, that is nothing but the east. So how this east was predicted? The east was predicted based on two information. One is nothing but the previous word and another is nothing but the previous hidden state information, or the state information. So how we can able to represent it? You can represent it that the model passed the previous input and the previous hidden state, that is nothing but the H3. So now I can say that the H3 acts as a memory and it stores the information about the previous words of the model. So when I am passing this H3 into the hidden state H4, then I can say that this hidden state behaves like an memory which contains the information about the previous words. That is nothing but the contextual information present in this line. So as this contextual information is present inside this line is passed into the state, and thus though is passed into the state, so it can able to provide the output that is nothing but the east. I hope it is clear to everyone that how exactly this recurrent neural network behaves or works. What is the architecture of this recurrent neural networks? In a summary, we can say that this recurrent neural network is consists of an input layer, consists of an output layer, and another is called a hidden layer. In this case, the hidden layer is not a single hidden layer, it is consist of multiple hidden states. And basically this hidden state or the number of hidden state depends upon the number of words or the alphabet, number of symbols or the alphabet or the characters, etc. How exactly this hidden layer behaves, that we are going to discuss on. So as we have discussed, this first part or the first pass consists of the, second pass consists of sun, next is rises, next in, next the, and the output is the east. So in this case, we can summarize that each time or every time the model passes the input word and the previous hidden state, and this will give rise to the final output. So in final state, as already have discussed, the model passed the previous input and the previous hidden state, and based on this previous input and the previous hidden state, the blank, that is nothing but the empty space, can be filled, that is nothing but the east. So now, what the summary of this recurrent neural network? The summarization of this recurrent neural network says that it behaves or works on the principle of the hidden state. And this hidden state behaves like a memory. And this memory basically captures the contextual information present in the line. So that means I can say that this recurrent neural network works on the principle of the contextual information, and which is passed into the model by the help of hidden states. And basically the hidden state has the capability of storing the previous informations. That exactly what the recurrent neural network says. So if you look into this application of this recurrent neural network, there are many type of applications, and mainly it is used for time series application as well as text applications, where the information can be of any length. In case of time series application like ECG signal or EEG signal or PCG signal, the information can start from a very long back, and we are basically predicting what will be the next output. In case of text or in case of languages, audio or speech signals, basically the speech sentence are very big, and what will be the next word that we are going to predict. So basically for this kind of applications, this recurrent neural network is very popular to identify or to predict what will be the next one. So in case of weather prediction, natural language processing, language model, sentiment analysis, basically this recurrent neural network is used. Now we'll just look into the difference between the recurrent neural network as well as the deep neural network or feed-forward neural network. Already I have discussed. In case of a feed-forward neural network, there is a direct flow from the input to the output by the help of the hidden layer. So this architecture is represented by this left-hand figure. But what about the recurrent neural network? If you look into the recurrent neural network, there is a direct connection, or there is a flow of information from the input layer to the output layer to a hidden layer. So there is that means there is an arrow is present in the hidden layer. That means the information passed from one hidden state to the next hidden state. And basically this information can be represented as unrolled version of the recurrent neural network. And what is this unrolled version of the recurrent neural network that we are going to discuss in the next slide. So basically this will give rise to a looped connection. And what is this looped connection? Basically this looped connection of this recurrent neural network helps to identify the contextual information that is present in the sentence. Hidden layer is used to identify or to take the previous hidden information to predict the output. So now we'll talk about what is the unrolled version of the RNN. Unrolled means as we are basically making a rolling of some chapati or bread. So if you unroll it, then how it will look like? Basically, this hidden layer will become a linear structure. So how exactly it will look like? So if you just look into this diagram, so this is the diagram that represents the unrolled version of the recurrent neural network. So in this case, if you look into the bottom line, there is nothing but x0, x1, x2 up to x of t minus x of t. There is a mistake here. That is, this will be x of t plus 1, not t minus 1. So that means these are the different inputs that we are feeding into the network. So now this is h0, h1, h2, ht or h of t minus 1. So similarly, this is the output that is y0, y1, y2 up to y of t minus 1. So now in this case, just look at here. This is nothing but the input, this is the output, and this is the hidden state or hidden layers. So now this hidden layers, I have unrolled it. So that means this previous hidden information is given to the next hidden state. And basically this hidden state will provide the output. Similarly, this hidden information is passed into the next hidden state as well as the current that input, and this will provide the output. And this process is going up, and this is known as the unrolled version of this recurrent neural network. So now we'll just go back. I have just yes. So as we have discussed about the unrolled version of this neural network, basically this unrolled version of the recurrent neural network tells about the rolling out of the network for the complete sequence. That means we have to just unfold it, the network for a complete sequence. Now, what is basically this sequence represent? As we are talking about the sun rises in the east. So in this line, there are how many words are present? Based on that number of words, we can able to design a recurrent of that much number of sequence or the sequences. So we can say that the input sequence of t words. So t words considering that much number of words we are basically using. So input sequence of t number of words we are present. So that is 0 to t minus 1 number of layers. So one layer is corresponding to the each word. So in our sentence, that is the sun rises in the east. So corresponding to the each word, we are corresponding to one layer. So in our cases, that will be starting from 0 to t minus 1. So one layer is corresponding to the each word. So now how exactly it is working? So if we take the time step that is equal to t is equal to 1. In time step t is equal to 1, the output that will be y1, which will depends upon the input that is x1 and the previous hidden state h0. So how exactly it will be? So just look at this diagram, that is the unrolled version of this recurrent neural network. In this case, the output y0 basically depends upon the input that is equal to x0 as well as the initial or the h of initialization, that is h0. So based on this, it will basically predicting the output that is y0. In the second step, that is equal to in y1, what will happen? How y1 can be predicted? The y1 can be predicted by taking the input that is equal to x1 as well as the previous hidden information, hidden state information that is equal to h0. So predicting y1 basically depends upon the information that is h0 as well as x1. So this is the way that how exactly the recurrent neural network is behaving or the working. So that's what I have written here. In time step t is equal to 1, the output is equal to y1, and which basically depends upon the current input x1 as well as the previous hidden state information, that is h0. Similarly, if I will consider the time state 2, the output that will be y2 depends upon the current input, that is x2, as the previous hidden state information, that is h1. And this process will continue, and up to what point it will continue? It will continue up to the last layer, that is equal to t minus 1 number of layers. So that means it will start from 0 and it will continue up to the t minus 1 number of layers. I hope it is clear that how exactly the recurrent neural network is working. It works on the two inputs. One is called the input at the current time, as well as the previous hidden state information, that is nothing but the memory. That is basically nothing but the contextual information of the previous state. So now, how exactly this propagation basically happened? This propagation in case of recurrent neural network occurs due to certain weights, and basically this can be represented by the weight matrix. And what are these weight matrix? These weight matrix are nothing but U, W, and V. So here there is the notation U stand for input to hidden. So just look at here. This is known as the input layer. This is the output layer. This is the hidden layer. Basically, this hidden layer transforms the information or the contextual information from one state to or one layer to the another layer. So now there are three weight matrices are present. One is called U, another is called your W, one is called the V. So what is U? U is nothing but the input to the hidden layer weight matrix. What is W? W represent the hidden to hidden layer weight matrix. V represent the hidden layer to the output layer weight matrix. So now these weight matrices are responsible to predict the output. So now U is the input to the hidden layer weight matrix, W is the hidden to the hidden layer, and V is the hidden to the output layer weight matrix. Now we are basically calculating? We are calculating the hidden state information, that is contextual information, or that is called known as the memory. So what is this memory? This memory can be, or the hidden state at any time instant t can be computed by this expression, which will be represented by tan hyperbolic the into hyperbolic of u into xt. What is u? U is nothing but the input to the hidden layer weight matrix u. Xt is nothing but the input given at the time instant t, plus w. W is nothing but the hidden to the hidden layer weight matrix into h of t minus 1. H of t minus 1 is nothing but the previous hidden state information. I hope this line is very clear to everyone. That means what exactly we are passing to the next state or to the next layer? We are passing to the next layer, that is known as the ht. ht is computed based on the tan h u of xt plus w of h of t minus 1, where u represent the weight matrix that is connected between the input layer and the hidden state, and xt is nothing but the input that is given at the time instant t. W is nothing but the weight matrix which corresponding to the hidden layer, and h of t minus 1 is nothing but the previous hidden state. And this equation is represented by this expression, that is tan of h input to hidden weight into input plus hidden to hidden into previous hidden state. I hope it is clear to everyone that how exactly it is happening. So now this h of t will not able to predict what will be the output. Now this h of t will multiplied with vt and passed into a softmax to provide to the output that is equal to y. So what is this y? This y can be represented as, or the output can be represented at any instant time that is equal to t, is nothing but the softmax of v into ht. So what is v? If you look into this diagram, this v is nothing but the hidden to the output weight information. So hidden to the output weight information get multiplied with this h of t, that is called your hidden state information, and that will pass into the softmax. We'll talk about later that why you have taken tan hyperbolic x there and why you are taking softmax here. What is the reason behind that? So that we'll discuss later on. So just remember that h of t will be calculated based on the tan hyperbolic, and yt is calculated based on the softmax softmax. So now the softmax of hidden to hidden output weight is get multiplied with the hidden state at any time instant t to provide the output information, and this is called the output that can be obtained in case of a recurrent neural network, or that is known as the forward propagation of this recurrent neural network. Now this is more elaborately represented here. So here there are some three states have been taken, that is equal to x0, x1, and x2. So now x0 is associated with an weight that is equal to u. And similarly, this hidden state is associated with another weight that is equal to v to provide the output. So here is the initialization that is equal to h initialization w is present. So now what exactly h0 is computed? H0 is nothing but tan hyperbolic of u of x0 plus wh initialization. Now this weight will be given to the next layer. Now this h1 can be computed based on the input that is equal to x1 as well as the w. How it will be computed? That is equal to h1 is equal to tan hyperbolic of u into x1 plus w into h0. Similarly, this information will pass into the next that will be computed or give rise to the h2 information that is tan of ux2 plus wh1. So I hope it is clear to you. So now, what will be the output of this first layer? The output of this first layer is nothing but y0 here that can be represented by the submap of vh0, v into h0. But output of the that is x1, this second layer. The output of the second layer is nothing y1 here that will be represented. This third layer can be represented by y2 here that is h2. So this is the way how the information is passed from able will be the last output. So how exactly we can able to predict that the sun rises in the dash. So in this case, the way how exactly it is predicted, the last word that is nothing but the east. So this is the way how exactly from layer to layer information, that is the contextual information, is transformed from the one layer to the next layer and to provide the final output. I hope this slide is clear to you, everyone, that how exactly this information is. Now, we'll just look into the back propagation through time. That means how this information layer to layer in time. That means how we can able to predict the output. So basically, in this case, we can able to calculate the loss. So how to calculate the loss? Basically, we can compute the loss in case of each time step to determine the prediction of the output. So in this case, we have taken the that means recurrent neural network can use the cross entropy loss functions, that will be the loss at any time step t. So at any time step expression, that is LT is equal to negative YT into log of YT. What is YT? YT is nothing but the prediction get at the any layer of this recurrent neural network. And what is this YT? YT is nothing but the actual output. So just look at this expression. In this case, I can talk about only one loss function at any time step t. But if you look into the previous diagram, in this case, there are multiple number of layers are present. So for each layer, we can get a loss function, or that is nothing but the loss. So, but there are multiple number of layers are present. So what will be the total loss? The loss for the t minus 1 of number of layers can be computed as the summation of j is equal to 0 to t minus 1 L of j. So this is known as the total loss. So we have to minimize this loss values. So how to compute this loss? This can be propagated back through time to calculate the weights. So how this loss at any time step t can be computed? So this is nothing but the back propagation. Just look at here. In this case, there are 0 to t minus 1 number of layers are present. So 0 is nothing but the input. This h initialization is given. So based on this x0 as well as initialization and the weight that is associated with the input to the hidden and hidden to the hidden, it can compute y0. Now based on this y0, it basically depends upon the hidden to the output weight as well as v into that is equal to output weight with passed into a softmax functions. Now this will give rise to a loss that is equal to L0. Similarly, the second layer, and similarly t minus 1, that is nothing but your LT minus 1. This will be all summed up to give rise to a total loss that is present or that can be computed in case of a recurrent neural network. So this is known as the total loss that is associated with the recurrent neural network. Now, how to optimize it? So this back propagation through time or back propagation of time can be optimization done with respect to the U, W, and V. So what is U? U is nothing but the weight that is associated with the input to the hidden. weight W is associated with hidden to hidden, V is associated. Now we have to perform the optimization. This optimization is done by the help of gradient descent. What is this gradient descent algorithm? So in this case, we calculate updated weight to nothing but the initial V or the previous state V minus alpha, which is nothing but the learning rate with the gradient of the loss function, that is del of L with respect to V. So similarly, W can be computed as W minus alpha into del of L with del W. So similarly, the updated U can be computed as U minus alpha into del L by del U. So we are calculating the value of loss functions. Am I audible? Am I audible? Excuse me, am I everyone?
Yes, sir.
Okay, thank you. So now, what exactly this optimization we are doing? So in this case, we are predicting the output that is equal to YT. That is nothing but the prediction of the final layer. And how it can be computed? It can be computed that is the gradient of the loss of YT. So in this case, we are talking about the cross entropy loss function, that is the total loss that is minus YT log of YT. So if we take the derivative of this, that is a logarithmic function, that will be nothing but, we know that it will be 1 by x. So if we'll simplify this expression, that is the loss with respect to the prediction, that is we can get, that is minus of YT divided by Y of prediction T. So del of or we can say that the derivative of this loss with respect to the predicted output will be represented by actual output divided by the predicted output. So where YT represent the actual output and Y hat T represent the predicted output. So now how this propagation is happens, this gradients we have to calculate with respect to the three different weights. We have three different weights. What are the weights that we have present? We have the weight present that is known as the U, which is nothing but the input to the hidden, W hidden to the hidden, V hidden to the output layer weights. So now how we can able to calculate the steps in case of forward propagation. So as we are talking about the forward propagations, in this case, what is HT? This HT is nothing but the hidden state information or hidden state or the memory. How we have computed? Already we have discussed that hidden state information at any time instant t can be computed as tan hyperbolic into u of xt, that is u is nothing but the weight into the xt, that is the input at that current state, plus w into h of t minus 1. What is w? W is nothing but the hidden to the hidden layer weight with h of t minus 1. That is nothing but the previous or time instant context. Now, what is YT? YT is nothing but softmax V into HT. So what is V? V is nothing but the weight that is associated with the hidden to the output. And what is HT? HT is nothing but the hidden layer output at the time instant T. Now, after this, we are calculating this loss, that is nothing but the loss associated at the time instant T, that is equal to negative of YT into logarithmic of Y, that is prediction, that is this is nothing but the prediction. So this is called the loss. Now here we have to just make some little bit substitution of this variable that is known as VHT. I have taken as ZT for simplification of calculations. So now if I substitute VHT is equal to ZT, so this expression will boils down to Y, that is prediction, that is softmax of ZT. Now predicting this Y cap, that is equal to Y cap t at any instant time t, we are at the final layer of the network and we have to use the back propagation through time, that is the output to the input. So how we can able to do that is the first we have to weight would be V and hidden to the output we have to compute. So how we can able to compute these back propagations? So in this case we have to look into the two information. One is called your final loss as well as the final gradient. So what is final loss? This final loss basically represent loss over the all time steps. Already I have discussed that what is the loss over the all time steps. Just look at this diagram. You can able to understand that in each layer we can able to calculate a loss that is equal to L0, L1, L2 up to L of t minus 1. This will be summed up and this is known as the total loss in case of a recurrent neural network. Now that is nothing but the loss, or we can say that a final loss that is known as the loss over the all time steps. So this is nothing but the summation that already we have discussed. Now what is final gradient? Basically this final gradient represent the sum of gradients over the all time step. So what is the final gradient? So this final gradient can be computed with respect to V. So now what is V? Basically V represent the weight that is associated with the hidden state to the output layer. So how it can be computed? So this final gradient can be computed as del of that is known as the derivative over the loss with respect to the weight function, or that is equal to which weight? The weight is nothing but the weight that is associated with the hidden layer to the output. So how it can be computed? If we will expand this can be represented as del L0, that is L0 is nothing but the loss that is associated with the zeroth layer with respect to V, del L1 with V, del of t minus 1 with respect to V. So how it can be? So it can be represented like something like this, del L by del V, that will be summation j is equal to 0 to t minus 1, del of Lj. This is nothing but the final gradient, sum of gradients over all steps. So now already we have discussed this, that loss function that will be nothing but represented by this expression. Now, if I and yt is equal to nothing but softmax of vht, that will be nothing but softmax of zt. Now we'll apply the chain rule of the derivative. So because we cannot able to compute the gradient with respect to v, if you look at this expression, this is nothing but the loss function is this much, and y hat is represented by softmax zt. So we cannot able to compute the derivative with respect to v. So how we can able to compute the loss with respect to v? So we have to apply the chain rule. So what the chain rule says? So we have to take the derivative of this loss at the jth time will be with respect to y cap, that is nothing but the prediction, that is yj. Then take the derivative of the prediction with respect to z. What is z? Z is nothing but we have taken the variable as a the multiplication of the weight with the ht. Then the derivative of z with respect to v. So this is the chain rule is applied for the loss function del L by del V, which will be computed as j is equal to 0 to t minus 1 del of Lj with respect to the predicted output, derivative of the predicted with respect to g or jz, derivative of the gz with respect to the v, that is nothing but the weight that is associated with the hidden state to the output layer. So now we have to compute the each derivative, that how much exactly the derivative to be. So first part, so this is already we have discussed, or we have found out with respect to the chain rule, that is equal to del L by del V, that can be represented as j is equal to 0 to t minus 1, these representations. Already we know that the predicted output is nothing but the softmax of VHT. So here VHT is equal to nothing but j by del of and del of yi with respect to dz. So now we have to compute what will be the value. So now this value is represented here. So now this red line or red point can be represented by derivative of the loss at the jth layer with respect to the output.
Sir, I guess you're having some networking issues. We're not able to hear you.
Yeah, sorry, again disconnected. Okay. So as we are discussing that this equation will simplified into this expression. So now calculated the loss with respect to the weight that is associated with the hidden state to the output that will be represented. So now already we know that this if we take the derivative of yj into yt. So if j is equal to t expression, now we'll substitute this value in this expression. So if we'll substitute this value in this expression, the jth layer with respect to the predicted output of the jth layer with the zt. So now this value will be become equal to yj divided by yj respect to del zt. So I hope this is clear. So now del of L with respect to zt can be represented by this. Now this we have to substitute in this expression. So if we'll substitute this expression or this, go for simply y of j. So if Sir,
Sir, you
am I
are.
audible?
Yeah, sir, yeah.
Yeah, actually, my net was disconnected again and again due to some network
No
problem. I
problem,
have
sir.
connected.
No, we
Uh,
understand, sir.
Sorry for the inconvenience. So what we are discussing, just let me to explain once again. So just we're talking about y minus yt. What is yt predict that number of the output at the tth timestamp? And what is this yt? This yt is nothing but the actual output. So at this del L by del V, because we have to compute this V. That means we have to take the derivative of the loss with respect to the weight that is equal to V. So now if we substitute this value and we can go for simplification. So just this is the simplest mathematics that I have worked out here. So if we calculate this, this derivative of this loss with respect to the weight can be found out to be j equal to 0 to of layers present in the recurrent neural network. And yt minus yt. So this is by these expressions and just substitute it and with multiply ht. So what is this ht? This ht is nothing but the hidden state information at the tth timestamp. And how we got this value? This already we have computed. Zt, we know that we have substituted zt is equal to vht and just take the derivative of zt with respect to this v, then we can get ht. So now we have substituted this ht at here. So this is the expression that we got, that is the
Sir,
the output is this present. Okay, I hope. Yes, madam.
sir,
Yes,
your voice is
any questions?
breaking.
Yes, madam.
Your voice is breaking, sir.
But I hope voice is breaking. Actually, I have connected to my mobile data now. Just
Okay.
1 minute. Okay, madam. Just if any problem happens, just please let me know. Just interrupt me in between.
Sure,
So
sir.
as
Now
we
it's
have,
fine, sir.
yeah. So what we have computed? We have computed the derivative of this loss with respect to the weight that is known as the V, which correspond to the weight that is nothing associated with the hidden state to the output, that is a loss. That is the derivative of the loss with respect to the hidden state. That already we have computed. That is del of L with respect to del V is equal to J is equal to 0 to T minus 1, where T minus 1 represent the total number of layers, 0 to T minus 1 number of layers. That will be computed as yt cap minus yt multiplication with ht. So this is how exactly we have computed. So now this is the gradient that we have computed with respect to hidden state to the output. But in a back propagation, what we exactly have to compute? We have to compute all the weights. We have 3 weights in case of recurrent neural network. One is u, one is w, another is v. What is u? U is nothing but the input to the hidden state. What is w? W represent hidden state to hidden state. What is v? V represent to the hidden state to the output state. So we are calculating the loss in a back propagation. So now first we have computed the loss that is with respect to V. Now we have to compute the loss with respect to W. Then we have to compute the loss with respect to that is U. So this is the way that how exactly we are passing to. So now the second step we have to compute, that is the gradient with respect to hidden state weight. That is nothing but a W. So gradient of loss with respect to the hidden state weight can be computed as we have discussed in case of the weight that is V, that is represented by the final gradient, which is equal to the sum of the gradient over all time steps. If we look into our memory, just go back in our previous slides, how exactly the loss is computed. In this case, the loss is nothing but the sum of the losses of the individual layers. In this case, t minus 1 number of layers are present, 0 to t minus 1. Total is t number of layers. So now all the losses have been added up. It will give rise to the final loss. Now this final loss is computed with respect to the weight, that is V. Then we have to compute the that is loss with respect to W. Then we have to compute the loss with respect to U. So this is the way that we have to proceed. So already we have discussed that is the loss or the derivative of this loss with respect to B. Now we have to compute the derivative or the gradient with respect to the weight. So that we can calculate the final gradient, that is the del L by del W, that can be represented as del L0 by del W, del L1 by del W, that is nothing but the derivative of the loss at the first layer with respect to W. Similarly, t minus 1th layer with respect to W. So this can be represented as the total loss. That is the total gradient, that is the derivative of the loss with respect to W, can be represented as summation j equal to 0 to t minus 1 del of derivative of Lj divided by del W. So now how to compute it? That is the whole question mark here. How we can able to compute del L0 by del W? What is the idea? So we have to use the chain rule again. So already we know that if we talk about the 0th layer, this L0 can be represented as minus of Y0 log of Y0, where Y0 is equal to nothing but the softmax of H0V, and H0 is equal to tan hyperbolic of UH0 plus WH initialization. Just remember, recall our memory. So what exactly we are calculating? H0 is nothing but the hidden state information at the 0th layer. What exactly the hidden state information? The hidden state information represented as the tan hyperbolic U is nothing but the weight that is associated with the input with the hidden state into X0. X0 is nothing but the input given to the 0th layer plus W. W is nothing but the weight that is associated with the hidden layer into H initialization. H initialization is the initial weight given to the recurrent neural network that is at the 0th layer. So once you have computed H0, then we are calculating Y0. What is Y0? Y0 is nothing but the prediction at the 0th layer. So what is the prediction at the 0th layer? That will be nothing but the softmax that will be computed as H0V. And what is L0? L0 is nothing but the loss that is associated with the 0th layer that will be computed as Y0 log of Y0. So I hope it is clear to you that how exactly we are calculating the loss at the 0th layer. So now this loss we have to compute with respect to W. W is nothing but the weight that is associated with the hidden layer to the hidden layer. How we can able to compute? This can be computed as by computing or by applying the chain rule, that is del of derivative with of L0 with respect to Y0. Y0 is nothing but the output at the 0th layer. Similarly, derivative of the output at the 0th layer with respect to H0. What is H0? H0 is nothing but the hidden state information at the 0th layer. Then derivative of the hidden state information with respect to W. I hope this line is clear to everyone that the derivative of loss at the 0th layer with respect to W is equal to derivative of loss at the 0th layer with respect to the output at the 0th layer, derivative of the output at the 0th layer with respect to the with respect to the hidden state information, derivative of the hidden state information with respect to the W, that is known as the weight. So now, as we have understood this part, so now we can able to compute what will be the derivative of this loss at the first layer with respect to W. So how we can able to compute the derivative of the first layer with respect to W? If we apply the chain rule, then how much it will be? That is the derivative of the loss of the first layer with respect to the output, that is equal to Y1. What is Y1? Y1 is nothing but the output of the first layer. Derivative of this first layer, that is derivative of the output of the first layer with respect to the H1. What is H1? H1 is nothing but the hidden state information at the first layer. Then the derivative of this hidden state information with respect to W. That means we are calculating the derivative of H1 with respect to W. I hope it is clear to you. Now, what is del of H1 W? Already we know that this H1 information depends upon two parameters. One is nothing but the input at the first layer as well as the hidden state information of the previous layer. So now this again we have to apply the chain rule at this point. So if we apply the chain rule at this point, then this can be represented as the derivative of H1 with respect to H0. Again, derivative of the H0, that is the hidden state information at the 0th layer with respect to W. So now why we are applying it here? Because H1 is represented by the tan hyperbolic of U of X1 plus WH0. Again, we know that H1 is nothing but the hidden state information at the first layer, which depends upon the H0, that is nothing but the hidden state information at the 0th layer, as well as the weight that is associated with that. So H0 is not a constant, it depends upon a function. That's why it is represented like this. So now we'll just realize this information by the help of a graphical representation, how this optimization is happening in the first layer. So we are calculating the total loss. So now we are calculating the derivative of L1 with respect to Y1. That is nothing but what is Y1? Y1 is nothing but the output, or that is known as the predicted output of the first layer. Then derivative of Y1 with respect to H1. What is H1? H1 is nothing but the hidden state information of the first layer. Then after that, we are calculating the derivative of H1 with respect to H0, because H1 depends upon H0. So that's why we are calculating derivative of H1 with respect to H0. H0 is depending on the W. So that's why we are calculating del H0 by W. So in or we can say that the with respect to W can be computed by these representations. I hope anything you want to ask at this point. Yes, any questions? Okay. So now the similar way we can able to compute what will be the L2. So if we'll calculate the derivative of the loss at the second layer, then how it will be? So derivative of the loss at the second layer can be represented as derivative of loss with respect to Y2 into derivative of Y2 with respect to H2, derivative of H2 with respect to H1, derivative of H1 with respect to H0, derivative of H0 with respect to W. So now the derivative of this loss at the second layer with respect to the weight can be represented by this expression, that is derivative of L2 with respect to Y2, derivative of Y2 with respect to H2, derivative of H2 with respect to W, plus this complete information, because this H2 is again depends upon H1, again H1 is depends upon H0, and H0 is not a constant, depends upon the function. So that's why this can be represented by this. Now, just understand that what will happen if we will calculate the derivative of this loss at the t minus 1th layer. So how it will be? How exactly by or this can be applied to the loss at any time instant, that is starting from 0 to t minus 1. So we can say that this is nothing but the computation of loss at any layer Hj, that is Lj, and this needs to be traversed in a backward direction, which is illustrated in the figure here. Suppose I will consider a jth layer, and it will transfer from the jth layer to the H0 information. So how mathematically we can able to compute this derivative of the gradient? So this derivative of the loss at the jth layer with respect to the weight, that is equal to W, can be represented as the summation k is equal to 0 to j. What is this j? This j represent the jth layer in the recurrent neural network. That is nothing but derivative of Lj with respect to Yj, derivative of Yj with respect to Hj, derivative of Hj with respect to Hk, and derivative of Hk with respect to W. And this what exactly this del of Hj with respect to Hk, this can be represented by a multiplication of this way. How exactly cases, that is multiplication and these multiplications, and they will be summed up. So now this can be represented by this expression. So now what is del of Hj by del of Hk? That is nothing but the multiplication of m is equal to k plus 1 to j del of Hm, derivative of Hm with respect to del of m minus 1. That is nothing but the previous step. Just we have taken one example for j is equal to 3 and k is equal to 0. So what will be the value? Del of H3 by del of H0, which will be represented by derivative of H3 with respect to H2, derivative of H2 with respect to H1, and derivative of H1 with respect to H0. So this representation, that means the derivative of the loss with respect to W at any jth layer can be represented by this expression. So which will be represented by k is equal to j to 0 to j, that J represent the any jth layer, arbitrary layer, derivative of Lj with respect to del of Yj, derivative of Yj with respect to Hj, derivative of Hj with respect to derivative of Hk, and derivative of Hk with respect to del of W, and which again can be simplified in these representations, and this will be known as the final loss with respect to the W. So in this case, there are two summations are present. If you look into these expressions, one summation is starting from j equal to 0 to t minus 1. Another summation is starting from k is equal to 0 to j. What is this j equal to 0 to t minus 1? Basically, this represents the sum of loss across all time steps. And what is k is equal to 0 to j? This represents the sum over the hidden steps. So this is, there are the two, that means two sums are present in this final loss calculation of this with respect to the W. So I hope it is clear to you. So in this case, the final loss will be represented by these expressions. Already I have discussed this representation to you. So this I'm just skipping this slide, so you just can able to calculate this now. Already we have discussed in case of recurrent neural network, there are three weights are present. One is called input to the hidden state to hidden state, and hidden state to the output. Already we have discussed how to calculate the gradient from the hidden state to the output and hidden state to the hidden state. Now, how to calculate the gradient from the input to the hidden state? That is nothing but the U. So what is this U? This computing the gradient of the loss function with respect to U is the same as with respect to the W. But in this case, the derivative will be computed for the loss Lj with respect to U, and it traverses back to H0. So how it will be? So now we are calculating the derivative of this loss with respect to the weight, that is U. So what is this U? This U is nothing but the weight that is associated with the input to the hidden state. So how it will be? It will be represented by the similar expression how it is computed for or the W also. So just I have represented these expressions, and this is you can do it this calculation by yourself the similar way how you have computed for this W. So as we are talking about the back propagation in time, so there is a serious problem occurs in case of a recurrent neural network, which is known as vanishing gradient as well as exploding gradient. What is vanishing gradient? Vanishing means something disappears. Exploding means which is burst or which is gives a very high value. So what exactly is happening in this case? Just try to understand. In case of recurrent neural network, at the 0th layer, we are initializing certain weight. And if suppose we are giving a high value in the forward direction, the weight, that means weight is get multiplied again and again, and it will give rise to a very high value. This is nothing but the exploding gradient. So in case of back propagation, what exactly we are calculating? We are calculating the derivatives. That means we are back propagating from the t minus 1th layer to the 0th layer. So what exactly is happening? The weights are get multiplied. When a smaller value is get multiplied with another smaller value, it will give rise to a smaller value, and this smaller value is goes on, and at a certain point the gradient cannot be computed. This is known as the that is known as the vanishing gradient. We'll talk about more detail how exactly it is happening in case of recurrent neural network, that is vanishing gradient and exploding gradient. So basically what exactly is happening when we are computing this derivative of this loss with respect to W or U? That means how we are computing? We are computing in a back propagation, that is nothing but traversing back to the past hidden state at any time instant t. So that means if I have 0 to t minus 1 number of layers and we am calculating the loss at the jth layer, then I'm traversing back from the jth layer to the 0th layer. So this is the way how exactly I'm calculating the gradient. So basically we can say that the traversing back to the past hidden state at a time state t is dependent on the previous hidden state at the time instant t minus 1. So how exactly it will be? It is nothing but the derivative of the loss at the second layer with respect to W will be represented as derivative of the loss of the second layer with respect to the output Y2, and derivative of Y2 with respect to H2, derivative of H2 with respect to W. So that means we cannot able to compute the derivative of H2 with respect to W directly, because H2 is a function of H1 and W. and h1 is a function of h0 and w. That means there is a multiplication term is present with respect to the gradient. So how exactly it is happening? So for computing the derivative of L2, we basically requires what will be the initial hidden state information. How exactly it can be? Suppose I have a 50 layer recurrent neural network is present. If I have a 50 layer neural that is recurrent neural network is present, I have to compute the derivative of the loss at the 50th layer with respect to the output y50. Again, derivative of y50 with respect to h50, derivative of h50 with respect to h2, and this propagation will come till h0. So now what exactly is happening? We are going into a multiplication term, and finally we are getting the derivative of h0 with respect to w. So that means for a deep recurrent neural network with 50 layers, traversing is required till back to h0, and so RNN will not back propagate properly. Why it will not back propagate properly? Because when we are multiplying a smaller value with another smaller value, it will give rise to a very small value, and which cannot able to compute the gradient. And this is known as the vanishing gradient. So how we can represent, how it can represent mathematically? So already we know that the HT of that is nothing but the hidden state, or that is contextual information at the tth layer, can be represented by u of xt plus I can say that the hidden state information of the previous layer, so into w. So that is, this is the representation ht, that is negative of tan hyperbolic u of xt plus w of h of t minus 1. So each time we are moving backward direction, that means we are calculating the derivative with respect to h. So the derivative of tan h is basically bounded by 1. That means the derivative of tan hyperbolic is nothing but 0 to 1. So multiplication of a smaller number with another smaller number, it will give rise to another smaller number. So that multiplication of some smaller number at every step, when we are moving in a backward direction, leads to a gradient, or that is nothing but infinitely small number, and which computer cannot able to handle it. And this type of problem is known as the vanishing gradient problem. I hope what exactly the vanishing gradient problem in case of this recurrent neural network, because we are calculating the derivative of tan h. So when we are calculating the derivative of tan h, it will give rise to nothing but 0 to 1. So 0 to 1 is nothing but suppose we will take 0.5. Again we will multiply suppose another 0.5, that will become equal to 0.25. Again 0.25, it will get multiplied with another 0.25. Again it will reduce, and at certain instant or certain layers, it will become equal to very small. That is known as the infinitesimally small number, and the computer cannot able to handle it. And this problem is known as the vanishing gradient problem. The similar opposite things happens in case of exploding gradient problems. So multiplying weights and derivative of tan h at every time step and repeated multiplication leads to a smaller number and causes the vanishing gradient. So now, what will happen in case of exploding gradient? So, basically, in case of recurrent neural network, we are initializing the weights. Where we are initializing the weights? We are initializing the weights at the 0th layer. So if we are talking about, or if we will consider a very large number, so what will happen? The gradient will become larger at every time step when we are moving into the forward direction. So during back propagation, a large number are multiplied at every time stamp and leads to with a larger number, it will give rise to the infinite. And this basically leads to exploding gradient problem. And in order to overcome this exploding gradient problem, the solution is nothing but a gradient clipping. So that means we have to limit the gradient values within a certain range. Suppose we will take the range of minus 0.7 to 0.7. So that means gradient will be normalized. So how we can able to normalize the gradient? So this normalized gradient can be computed by taking a threshold with respect to G predicted into the G predicted. So this is the way how exactly we can solve this issue. Now, just we have discussed what is the recurrent neural network. This recurrent neural network consists of or can able to identify the contextual information from the past time steps to predict the future outcome. So we'll take one example of this. Suppose I want to generate a song. I can say, what a beautiful D dot. So that means what is the value of this dot? So in the first time step, the recurrent neural network can able to predict what will be the dot. That is nothing but in the it can say what a beautiful day, DA. So what will be the next instant? In the second step, it can able to predict what will be the next output, that is equal to I. So this is the way how exactly the prediction of new character at each time step is done. Similarly, we can also use new word prediction, that is called a word level recurrent neural network. So we'll just talk about that a music generation, so that is called character. Suppose I generate the word that is known as the law. So the input is nothing but L. So now what exactly the recurrent neural network compute? The recurrent neural network will compute the probability of this next word to be predicted. So what exactly? And I have given the first letter that is equal to L. And what will be the probability of the word the L to come after L? That is nothing but 0.0. What will the probability? Nothing but 0.9. What is the probability of E to come after L? That is 0.1. So the way of having the higher probability after L is nothing but O, and which is equal to 90%. So the probability of distribution will decide that what will be the next alphabet will come after this L. So that is equal to 90% of the time the O will come after L instead of E, which is having the 10% of probability. So this is the way that predicting the next character by sampling from the distribution and add some randomness to the output, and which will helps into generating the music. So how we can able to predict the character, that is in this case, the prediction of the character in the next time step was fed from the previous time step, and the previous hidden state as input to the next character. So we'll just look at this example of this. So initially we have given L to the 0th layer, that is x0. It can able to the predict the output that is equal to O, and this will give him to O to the next, and it will predict the output that is equal to V. So this process will continue. So that means the previous hidden state as input to the next character will give in to the generation of the music or the generation of the new word to be done. So if you look into this recurrent neural network types, there are many types of recurrent neural networks. Gated recurrent neural network, gated recurrent unit, time distributed layer, or convolutional LSTM 2D layers. So we'll talk about one by one what is called long short-term memory network. So before coming to this long short-term memory network, we'll just look into what are the different type of architectures that is associated with a recurrent neural network. The different type of architectures, the first one comes in this category is one-to-one mapping. So what is this one-to-one mapping? There is a single input map to a single output. That means the output from the time step T is fed as the input to the next time step. And basically this one-to-one mapping is used for generating the songs. There is a one-to-many mapping. What is one-to-many mapping? This is the single input is mapped into a multiple hidden states and multiple output values. So in this case, the single input is mapped into multiple hidden state and multiple output values, which basically share the previous hidden state across time, not the output. So in this case, it will provide the previous hidden state information across time, and this type of architecture is used for generating the image captions. Next is many-to-one. In this case, the sequence of input is given, or many sequence of input is given, and it maps into a single output that is known as the sentiment analysis or sentiment classifications. There is a many-to-many mapping that basically used for maps a sequence of input of arbitrary length to a sequence of output of arbitrary length. Basically, this is used for language translation, or that is audio generation, or that is a conversation between the robots. So now we'll look into what we have discussed in today's session. So if you look into the question, so what is the difference between recurrent neural network as well as feed-forward neural network? What are the different process of each recurrent neural network? What is vanishing gradient able to overcome this vanishing gradient problem as well as exploding gradient problems, as well as the types of recurrent neural network architectures? So in this case, we are discussing about the feed-forward recurrent neural network. There is a two-way of recurrent neural network that is known as bidirectional recurrent neural network. What is bidirectional recurrent neural network? We'll start this discussion with respect to an example of this bidirectional recurrent neural. Suppose I'll discuss one line. Dr. Vijay Lakshmi lived for 20 years in Dash. So she is good at speaking Tamil. So if I look at this statement, what will be the word that can be filled in this case? In this case, if I want to pass the information, Dr. Vijayalakshmi lived for 20 years in Dash, then this statement cannot be completed, cannot be predicted. So we have to use a certain kind of recurrent neural network in which the future can able to predict the back. So she is good at speaking in Tamil. So if I'll tell or if I'll utter this word, so she is good at speaking in Tamil, there is a prediction that she lived in Tamil Nadu. So this recurrent neural network cannot fill the gap. So in which can able to predict the output by looking into the futures or by coming back in the backward direction. She is good at speaking in Tamil. So that's why there may be a prediction that she has lived in Tamil Nadu. So this is the way that how this bidirectional recurrent neural network is working. If you look into this architecture, just look at this architecture. In this case, there are multiple number of layers are present. It is starting from t-1 number of layers to the t+1 number of layers. Here 3 layers I have taken. So in the forward direction, it is moving from the 0th layer to the last layer. In the backward direction, it is traversed from the last layer to the beginning layer. So this is the way how exactly the bidirectional recurrent neural network works. So in bidirectional recurrent neural network, there are two paths present. One is called beginning to the end, another is called end to the beginning. And this basically able to, or this type of architecture can able to predict what will be the output or what will be the output based on the future context. So just we'll talk about this bidirectional recurrent neural network. It is nothing but two different layers of hidden units consist of. So one set of hidden unit is consist of input to the output, and another set of inputs that is basically represent from output to the input. So in other way, I can say that there are two passes are present. One is from left to right, another is from right to left. So now, how exactly it will work on? So this principle is working on hidden state values are shared from past time step to the future time step. That means it is nothing but 0 to 1, 1 to 2, 2 to 3. So this is nothing but a forward hidden layer or the past time steps. Another is called future time steps. That means we got the future information first, then we are going back into the backward directions. So that means in backward hidden layer, the hidden state values are shared from the future time step. That is nothing but Z3 to Z2, Z2 to Z1, and Z1 to Z0. So this is the way how exactly this bidirectional recurrent neural network works. So it consists of two recurrent neural networks, or that is known as the hidden state values. One is in the forward direction, another is in the backward directions, or we can say that one is in the past time step, another is in the future time step. That means past time step represent, we are taking the past information of the context to predict the future informations. In case of future time step, we are taking the future information to predict the past values or the past informations. So there are two time steps present in case of two directional, bidirectional recurrent neural network. One is called past time step, another is called the future time steps. So one is from left to right, another is from right to left. And this is represented by this diagram. So already we have discussed. If you look into x0, x1, x2, x3, these are nothing but the input layer inputs given to the different layers. And H0, H1, H2, H3, these are nothing but the forward hidden layer informations at the different time instant. And Y0, Y1, Y2, Y3, these are nothing but the outputs that is predicted from these different layers. Now, what is Z0, Z1, Z2, Z3? These are nothing but the backward hidden layer informations present in this bidirectional recurrent neural network. So already this is the diagram that already we have discussed. So this is the same diagram represented in a different way. Now, What is the use of the bidirectional recurrent neural network? Already have this.
Yeah. Thank you, sir, for your detailed session on optimization strategies for deep learning models. Next, we have Ms. C. Nagalakshmi, ma'am, Vice President of Software Development, Bank of New York Mellon, for the session on advanced CNN architectures for clinical datasets. With over 15 years of experience in AI-driven financial systems, cloud computing, and deep learning applications, she has been instrumental in developing advanced AI solutions for data security, risk analysis, and on enterprise automation. She has specialization on AI-driven security, resilience engineering, and data analytics. She has led high-impact projects on automated risk management, real-time fraud detection, and predictive analytics. Her contributions to deep learning architectures have enhanced the efficiency of financial and healthcare AI models. In this session, we'll discuss advanced CNN architectures for more reliable AI-driven clinical predictions. Over to you, ma'am.
Thank you so much. Hi, nice meeting you all. Okay, let me share my screen. Okay, so a little more about me. So currently I'm part of AI Hub project in Bank of New York. So we are building like on top of like large language models. We are building automated legal paperworks, like how we can, if there is any memorandum of understanding or any legal document that comes in, how we can better provide solutions to the clients. So and like recently an AI project of ours like has achieved like $1 million savings to the company. So we are exploring more on like savings and how we can automate things like that. So right now, like today's session, I am going to focus on like CNN and also like how you can develop, like how you can architect solutions when it comes to enterprise level problems. Like, when you wanted to like, for example, for 1 million customers, like how you can develop, like how you can think on that level for 1 million customers, maybe for 10 million pings, like for 10 million requests to handle, like how you can handle like that. Because I'm going to talk some real time application as well, because it's going to help you like think in bigger levels. Like when solving enterprise level problems, like when it comes to like, okay, your solution is going to be deployed in different nations, and also it's going to handle large amount of users, large amount of requests, how we are going to handle it. So I'll be touching on that as well. So we'll see. So what CNN means? It means like learning pattern from images and improving diagnosis accuracy and speed. So CNN plays like critical role in diagnosing diseases like, life-threatening diseases like cancer, pneumonia, and other disorders. You might be asking like, okay, our doctors do the same thing. Like, why do we need a computer to do that? You see, like there are like I myself is part of like being subjected to medical errors. It happens very often, not getting diagnosed properly and not getting treated at the right time, not giving treatments to the right time. It's life threatening, and medical errors are not being like discussed upon because it's very sensitive matter, but at the same time it's life threatening sometimes actually. Like, can we trust AI in this? That's the question that we can ask. Like, can we trust AI in this? Not fully, but we can, take the uh, take the suggestions given by it, make the diagnosis given by it, and then apply the doctor's own like knowledge in that. Like, so these kind of advancements are happening in like major hospitals, like combining the expertise of doctors and also in using AI. So it's majorly used in like X-rays, MRIs, CT scans, and histopathologies to detect abnormalities. Okay, if you can think about like what could be the problems in these kind of medical imaging. The problem is like when you research about disease or anything, you have to have a huge amount of data set in order to say, oh, this is what it is. Generally, you should have analyzed like huge amount of database. Um, but that's sometimes impossible. For example, particular region people are vulnerable to few things, but few other people in a different region are not vulnerable to the same causes, or like they might, whatever seems to be normal in one particular region seems like abnormal in other particular region. For example, if you are applying a CPR to a kid, right, you'll be applying in a different area than when you're applying to an adult. Actually, if you are applying a CPR to a kid, uh, to a kid where you're applying to an adult, it could be life threatening. So it varies. The variety is the problem, and also it has to handle large amount of database, large amount of data, and it has to vary, and it has to consider all those aspects. um, like is that possible? Yes, over a period of time it's very much possible. Like we see, like as humans, it's not just our knowledge, right? Like we get it from our ancestors. We haven't like discovered everything on our own. We get the knowledge from teachers, lectures, and so many different. So over a period of time it can get accumulated and it can mature, but right now it hasn't like grown to that level. um, there are various aspects to it. For example, in US or different countries, patient sensitive, like data will be treated very sensitively. Patient is very particular in, like, like what are you doing with my data? So they do not want to be like shared, analyzed, or anything like that. And of course in India we have like lesser guidelines on that, but still we have to get a patient consent to use his data in any research, or like to consider for in order to train AI, right? That's a major challenge that we face actually. And we have to go through all. For example, if we are having enterprise level solution like that, and you are considering it cannot be on random data. So whatever the data which is available right now, can we train on that? Yes, we can train on that. Can the AI take more mature decisions on that? No, it's not possible. So training the AI based upon like dodging regulations like HIPAA, GDPR, like these are like regulations set by governments um, not to use like patient data without their consent, because it can be easily be like it can be easily like compromised actually, when it gets into wrong hands actually, right? What are the components of CNNs? The components are convolutional layers. So it acts as feature extractors and detecting edges and textures, and activation functions. So activation functions, these are the most essential ones. And I'm going to talk a little more about it because it introduces a non-linear in order to learn the complex patterns. And there are like common functions are there, which is rectified linear unit and sigmoid and tan. So these detect hierarchical pattern edges, textures, which ensures the effective learning in deep networks. And about the pooling layers, it reduces the image size while retaining the key features in order to make the model effective actually. And the full connected layers, it converts the extracted layers into a final prediction, like how is it like healthy or like unhealthy individuals. So there are like different levels of feature extractions in CNNs. One is like low level features, something like, okay, can we detect like edges and lines like that? And mid level features are like detecting textures and small structures, and high level features are like complex, like can we predict tumors, malignant or tumors like that? Yeah. So why like what is the limitations of basic CNNs, and why do we need advanced architecture? For example, we talked about the data sets, right? Like when we get a data set, getting data set is a major challenge in hospital data. So when we get it, like in the basic CNNs, we have to make the models memorize instead of generalizing. For example, right, like in order to make you understand, so what Google does is like keyword search, but what ChatGPT does is like semantic search, right? Like, okay, so I wanted to search about Tyagaraja College of Engineering. Maybe like I wanted to know about like more details on that. So so what, besides Google, what does ChatGPT does is like more. It does the semantic search. It tries to understand. Maybe it doesn't have to be the same keyword that you prompted, but it goes and search the meanings and then tries to understand and then finds it, right? So instead of like memorizing the models, can we generalize and try to understand it more? So that has to be done, right? And the next thing is like interpretability, like how we interpret the data. For example, like more doctors, like if you see, like some doctors would say like don't ask questions based on Google, right? Like, so clinicians doesn't trust because they rely more on their experience, like some clinicians. So how can we make them adopt? For example, a big hospital, imagine something like Apollo, right? Like, big hospital, if they have a mandate to use CNN, then like not a lot of clinicians would go and look into it actually, because they would rely on their own judgments, right? So that's one of the major drawbacks. And the computational inefficiency. Oh, this is like, for example, if you have an idea to create a CNN, right, like on your own, and you wanted to give it as a free application, you wanted to create an app and maybe like do it in App Store. What do you think your major problem would be? It's like creating a high-end graphic processing unit or like high-end architecture. For example, if it's going to grow, then it's going to cost you money, right? Like, that's the problem. So for all the startups that you see, that's one of the problems. Like, oh yeah, they have ideas, they can implement it. Can they scale it and then like sustain like more requests? And that's going to be a problem. Like, when you not even a startup, like just when you create an app, um, okay, you have got a great idea and you have implemented, but do you have the architecture that's going to support? You might say like, yeah, yes, like why not? Like, how much it's going to cost per day? It may cost around like $10,000, like easily. So if it's going to be a fully scalable, we will discuss more on that. But so that's one of the limitations that we have. One second, let me minimize this. Oh yeah, okay, sorry about that. Okay, so these are some of the advanced CNN architectures that we have. One is the residual networks. So it addresses the problem of vanishing gradients. So we will discuss more on the vanishing gradient problem. And the other one is densely connected CNN. It improves the feature reuse by connecting all layers. An efficient net. It balances model depth, width, and resolution for better efficiency. Vision transformers uses self-attention instead of convolutions for better global context. Okay, we'll be discussing more on this. Okay, what do you think is vanishing gradient problem? Because in deep neural networks, so in deep neural networks, what do you think, like deep neural networks? For example, in human brain, in like it's got from it's the idea is gotten from like how we process information, human brain, right? Like how we learn from from one layer to the other, and then we improvise based on whatever the new learnings come in. So in deep neural networks, so as the data moves through multiple layers, the gradient, actually it's the weight, becomes extremely small. So uh, this creates a problem of like learning for the deep neural networks to be very slow and making the training inefficient. For example, in sigmoid and tan, the input values are from 0 to 1 or -1 to 1, so which causes gradients to shrink. And when the weight updates become tiny and the network struggles to learn deep learning representations, how we can fix it? Using ReLU architecture, we can fix it because it maintains stronger gradients, and also by implementing batch normalization to stabilize activations, and also by using residual connections to help gradients flow through deeper networks. Let's see. What is ResNet? It's the residual learning for deep neural networks. Let's see. It's created by Microsoft researchers, and it allows information to bypass layers. And it makes training for deep networks like until 50 plus layers, and it's very stable and effective. For example, the clinical applications is like using chest x-rays to differentiate COVID from pneumonia and healthy cases, and also for brain tumor segmentation. So it also identifies the MRI scans with high precision. And DenseNet. DenseNet means like densely connected networks. It helps to enhance feature reuse. And for dense connectivity, each layer gets input from all previous layers, improving information flow. Benefits such as fewer parameters and reducing computational load. Clinical applications are diabetic retinopathy detection, identifies retinal abnormalities from eye scans, and histopathology is like classified cancerous and non-cancerous tissues with higher accuracy. Sometimes like sometimes few tissues are grown which cannot like which is not malignant, right? Like can we identify those? So that's easily done actually. And efficient net for scaling CNNs very efficiently. So this is developed by Google Artificial Intelligence. And let's see. So it adjusts the model depth with resolution simultaneously for efficiency, and it makes it ideal for mobile and cloud applications. So what are the clinical applications? It detects pneumonia and chest x-rays with high accuracy, and it classifies the breast cancer. So it improves early detection from mammograms. About DenseNet, so this is proposed by Huang to enhance feature reuse. The dense connectivity ensures like each layer gets input from all previous layers, improving information flow, and benefits requires fewer parameters and reducing computational load. Clinical applications are diabetic retinopathy detection. So this identifies the retinal abnormalities from the eye scans, and histopathology analysis. It classifies the cancerous versus non-cancerous tissues with higher accuracy. Efficient net. Scaling CNNs efficiently. Key features are developed by Google AI and compound scaling. It's like it adjusts the model depth with resolution like for efficiency. Ideal for mobile and cloud applications. See. And vision transformers in healthcare. Like why vision transformers are needed? Instead of scanning images like CNNs, visual transformers analyze the entire image at once using self-attention. This allows them to capture long-range dependencies more effectively. So the clinical applications of brain tumor segmentation, more effective than CNN for large and irregular tumors, and organ detection in MRIs, improves localization of anatomical structures. Challenges in deploying CNNs in clinical practice. Major challenges are data scarcity, like many diseases lack sufficient label data for training. So this we have discussed in length. Yeah. And explainability and trust. So like clinicians still need confidence in AI-driven diagnosis. Probably, like, I think they would apply their own judgment, like, okay, is it like still is it still clear or not? But like so far what I have heard is like it does better diagnosis than clinicians actually, because human errors like are very like there are much more human errors than AI-driven diagnosis. And the computational costs, we have discussed about it. Like, for example, you need expensive and highly scalable graphic processing unit in order to deploy something like CNN actually. So that requires like more expensive. So why would any hospitals would require like CNNs or anything? They wanted to reduce cost, right? Like they wanted to reduce cost. At the same time, they wanted to enhance the treatment, but at the reduced cost. But like um, deploying uh, deep models, like if it's going to expand hospitals' finance structure, it's going to impact their net profit, right? So that's also a problem actually. We discussed about regulatory hurdles. So more other than India, like in India as well, right? Like there are like a lot of regulatory is there. A lot of regulatory is like how do you handle patient data, and um, if the patient data is not like, if for example if you are just getting like first name last name their date of birth, and it has to be like encrypted and stored in a secure way, uh, and it has, and at any point in time government is going to like come, like they'll ask like how you are storing the data. For example, in financial sectors, like the what I have worked on, so we get multiple regulatory from governments, like we report to governments like, okay, how we are actually taking the data, storing the data, for example trade related data, how we are storing it, like we send all those information. For example, if it's related to trade, and like few hours of downtime is going to cost several $1 million, sometimes $1 billion. um, that like that kind of sensitive applications that I have worked on, that that creates a like huge problem, not just for the company, right? It's for example, when you're responsible, when your trading application is responsible uh, at that level, which runs NSE or like stuck, like in that case the government like scrutinizes a lot. At the same time, even if it's a airplane company, if some airplane goes down, any airplane, like let's just imagine, like, so I worked in Boeing air, like remember 737, so when the airplane goes down, like Trump declared like no more flying this particular model, no more, like any model that's going to fly, that's going to like that's planned to fly, it has to be stopped immediately. Because you employ AI in there, and it's not, and it's going to create a mistake, it's going to cost lives. And government is responsible government is responsible to use AI or any technology responsibly. For example, like companies are like, okay, it's cool, like they employ new technologies, um, to improve efficiency, like can they do it like more more responsibly? So these regulations make like create checks to companies or any other organizations, right? Any other organizations, they make sure they have these regulations so that it cannot be abused. For example, patient data, you're taking a patient data which can be used in multiple ways, right? Like, just imagine like how else can like we can abuse patient data. It can happen. So there are like plenty of regulations are there when you're like taking a patient data. So you have to get consent from the patient, and that has to be, if you are developing a software like that, then you have to make sure that you are getting a consent and it's part of your application actually. Next is solutions and future directions. Okay, so how we can address these key challenges? Using the pre-trained models to reduce training data needs. Yeah, so these pre-trained models, for example, right? Like, so after this ChatGPT came, and oh yeah, so there is, and they have trained it for a while, and it's good. But for a financial institution, like for a financial company like Bank of New York, can we like straight away go ahead and trust AI with all our data? It's impossible, right? Like we cannot use, any organization cannot use the shared, like can you go and like upload a data file and then ask you AI to decipher the information for you? That's impossible, because that's against company rules. Like you cannot send the data outside company. So now how we can train in such cases, right? Like we buy it, and then we have our own models on top of it. For example, in Bank of New York, we have Eliza. We call it Eliza because like it's our own thing actually. So we train Eliza, like we train Eliza, like by uploading all the data related to the bank to it, and then like for example legal document, what is the proposal that you can give, what is the modifications that you can add. um, just go through this and like send out a proposal, like how it is different from it, how you can like increase the revenue. So all these data, like now how we can achieve, now we have to train, which is already there, but all the infrastructure has to be within BNY. It cannot go outside BNY, right? Like the data has to be controlled within BNY, and data cannot go outside. We cannot share the data. So we takes we take what's already there and then train on pre-trained model. Like we take what's already there and we train it. So for example, when we created ELISA, now it can handle. So we don't, like on top of it, all the data resides within BNY, Bank of New York. At the same time we use AI a lot. Okay, next is like few shot learning. So now this trains models with minimal data. And next is the federated learning. This allows hospitals to collaborate without sharing sensitive data. And hybrid models combines like CNNs and BITs for better performance. So these hybrid models you apply like everywhere actually. So what's best in CNN, what's best in BIT, we can apply it. We will discuss more on like how, like um, in a more use case basis and in the following slides. Uh, for example, like the federated learning, right? Um, how we can achieve this? For example, for example, if I have created something like episode, like which goes through legal documents and everything, like can we go ahead and what is there in the current market, like can we mimic the functionality over there. In order to mimic, like, can we buy it for a shorter period and then build our own, like, in-house product? For example, TCE also has like in-house products, right? Like sometimes you create like by your own creativity, like you find out something, like you discover or innovate and then create a new product, or like you see what's there in the market and then you try and mimic. In that case, like when you're collaborating with a different entity, right, like what's the amount of data that you can share? That's a major thing actually. The moment you share sensitive data, it's going to create problem, right, to the enterprise. So that's and it will be controlled by different levels. In an organization, it's controlled by different levels. You have to seek all the approvals. Like you will be seeking all the approvals in there, like, okay, this is what we are going to share, like, and mostly it'll be non-IT managers, MDs, like that, like what is the level of data that you're going to share. Okay. And when it comes to training the models with minimal data, what are all the data that's available in free internet? Like whatever the data that's already there, it's available. So we have to use all of them as part of our training our models actually. Okay. The case study. Okay, for the data set, whatever the Chester's data sets containing COVID-19, pneumonia, and normal cases, so that we can use it. And the models used are like, okay, ResNet 50 model fine-tuned for classifying the lung infections. The performance metrics, it measures around like 98 percentage, and for sensitivity, for the positive cases, it's like 95 percentage, and specificity, it's like ruling out the negative cases is like 97 percentage. Okay, so we come to the main part, which is relevance to advanced CNN architectures and clinical datasets. Okay, now let's assume like you have created you have a CNN which you're going to deploy it for. You have planned a CNN which you're going to deploy it for Apollo Hospital, chain of hospitals, which is going to be all over India, maybe all over the world. Some chain of hospitals which is all over the world. So what are the things that you like consider? One is like we discussed this before, it requires high performance computing and it has to have efficient data pipelines. Right? And like scalability. Scalability is like, okay, as and when we wanted to train the models with more accurate, that means we have to feed in more data. As and when we feed, for example, let's assume like you started it today and then you started feeding data now. After 10 years, like how it's going to grow after 10 years, after 5 years, how it's going to grow, like what is the amount of data set can you predict until that time? So we call it like, writing envelope. Okay, now I have this much amount of data, like what is the proposed growth for the next year in 6 months, what is the amount of users that's going to increase, and how the data is going to grow. So now like you have to compute it and then like uh, decide upon the scalability, right? And load balancing, for example, if you see, I ask you to develop something and then you're like, okay, so I have like one server, two server, I have like two servers. Now the code is going to be the code is like web server is going to be in one server and database is going to be in another server. Maybe I created a microservice architecture. Now, what's the problem with this architecture? One is like if the load is going to get heavy, then it's going to bring the server down, right? It's called single point of failure. Now you have created a architecture. After a while, it's unable to handle the data. It's going to poof, die. Like it's not going to respond anything. And then, which is a major thing, right? Like for example, for anything, like for any critical application, your availability has to be higher, right? And next is how we can optimize CNN workflows with system design is like, first you have like cache for the faster training. Like you have to store pre-computed feature maps in order to reduce the redundant computations. If you are going to like every time you're going to go on like query the million data sets, it's not going to retrieve like faster results. User going to wait forever to get any computed results, right? Like how we can get, for example, um, um, like we have to have our own caching mechanism, like how much, for example, maybe simple API, right? Like you create like fewer APIs, right? Then you can decide how much on API level you can even like how much cache it can handle. And after a while, like can it be replaced and how it's going, you can design on that. Next is database design for larger data sets. So NoSQL database like MongoDB, this stores unstructured data image efficiently. And so NoSQL, the beauty of NoSQL database is like, the one thing that I like most is like the cost. The cost is very less when compares to relational database. And also we can do the hybrid model in the sense, okay, any architecture which comes, what's best in relational database, what's best in non-relation database, can we combine and do it? We are going to discuss more on that, but like, can we combine and do it? And next is distributed training. The horizontal scaling with multiple GPUs accelerate CNN training. Do you know what's like horizontal scaling and vertical scaling? Yeah, maybe we will discuss more on that. Uh, Vertical scaling is something like, for example, you have like, there are two concepts, right? Like one is on-prem and another is cloud. Okay, on-prem, what is on-prem means? On-prem is like, okay, in Bank of New York, I'm saying like, I'm going to have my own data centers running in my own company, not going to give it to anyone. Okay. And there's a cloud, like for example, AWS, um, Azure. Now I buy like cloud and then we can make it as hybrid as well. But I say like, these are the data centers that I'm going to own. These data centers, like, okay, it doesn't have control, and can it be like can it contain only my company data, and that can be done. So for example, if you are saying like, okay, in on-prem, this is the difference between on-prem and cloud. I think, I hope you understand. Now for on-prem applications, uh, you're administrator. Imagine that you're an administrator. Now you're saying like, okay, it's going to have 5 data centers, and this is how my database is going to run. This is how my load balancer is going to serve the request. You have designed everything, but you have decided only on 5 data centers. So as and when the request increases and you have to increase your computation power, what you're saying, you're like adding additional CPU, adding additional RAM to the data centers. Okay, because it's like, it solves a problem at certain level. Okay, how this can be like, how do you think this can be applicable? For example, if you're doing for a small clinic, for example, tomorrow that you are developing this application for a small clinic, and then the doctor says like, this is the clinic that I run. I don't have future plans to expand or do anything, but I wanted to have the best AI, technology. Then okay, then you can create a replica, maybe make sure everything gets backed up, um, just in case if anything like crash or anything, maybe just you create a replication. Probably you'll have like vertical scaling, like few data centers, you keep few data centers, and then you just for a clinic or maybe 1 or 2 clinics, and that's for maximum that you can do. But when it comes to more than that, like it's going to be large amount of data, then you have to go for, you'll be considering horizontal scaling, like okay, adding more machines and then distributing the load. Okay, the problem with this is you have to any like uh, for example, you are submitting a request for data center. It's not going to be like immediately like delivered and then you can go ahead and settle. In an enterprise level, I'm saying, like in an enterprise level, it has to go through several approvals, and then after that came the configuration, and everything takes time actually. And employing people to like run the machines and making sure it gets administered properly. Again, the problem is with like um can humans handle like horizontal scaling, vertical scaling properly, and then keep the machines like up and running for all the increasing load? That's not going to be possible for like in a very huge application which is going to handle like millions of requests at the time, right? That time you consider like auto scaling. Auto scaling is like dynamically adjusting resources based on demand. This seems like a magic, right? Like, okay, this uh, today so many requests come, and it's going to increase. Like more allocation is going to be done, and it's going to serve the requests. That sounds fun, right? But the problem with this is like you can you the problem with this is like uh it's going to it's going to increase based upon the request. For example, we had a problem this week, like 4 days before. The problem is we were asked to update, like there are like some failures were there, several thousand failures were there, like all of them have to be retried. And then we were like, okay, there is like 2700 failures are there, and we did it for one case and it worked. Like then we did it for like 5 files, we retried, it worked. Then we were like, okay, if we retry everything, then it's going to solve the problem. Problem is like, okay, we retried everything. We are like cloud based application. You know how much it costed? $110,000 for 2,500 requests, because it's unable to handle like 2,500 requests at a single time. And then the problem is like the monitoring was not properly configured. When it exceeds this particular limit, it has to like seek approval from the higher managers. Can we run this kind of load? Anyhow, it's in production. It started allocating on its own $110,000, which is closer to 1 crore per day. That's the expense. And like all the MDs have to answerable, like why this thing happened. Because like it can go to that level actually. Like when you do auto scaling, you just go ahead, like today, go just create a free account in AWS, Azure. It gives you 365 days. You can deploy and then you can run your applications on your own. Okay, if you forget it and then you create some concurrent relational database, something like that, you forget it and then go to sleep. You have like, it doesn't get like let you create until you provide your credit card. Okay, you have to give your credit card, because when you overuse or like beyond that level, then it gets billed. That's how the free account works for 365 days. You go to sleep, come another day, it's going to cost you $10,000, which is like, it's $10,000. Yeah, it's more money. 8 lakhs, like single day. if you forgot to like shut down, you try to run an application, you test it, and then but you forget to shut down, it's going to cost you that much money actually. You just try just give random credit card and then you can try that actually. It'll be fun. Next is load balancing. Okay, why load balancing is important? It distributes incoming traffic across multiple servers, and it prevents overloading a single server, and it enhances fault tolerance and availability. Okay, the load balancing algorithms, you must have learned this like round robin algorithms, least connection algorithms, and weighted load balancing algorithms. Round robin is like as and when the request comes, it assigns to the server sequentially, and least connections are like it routes traffic to the server with fewest active connections. And next is like weighted load balancing. It assigns requests based on server capacity. So now, for a cloud related application, right? Like it lets you select which algorithm like round robin, least connections, or weighted load balancing. You can select your own load balancing technique, and then you can assign it. And there is another thing, like there is a gateway, and in gateway itself, like we can configure load balances. That's also a provision that's there. You might be knowing like gateway, like from where it actually it reduces like from which kind of servers. For example, how do you configure gateway in your application, right? I say, okay, this is an internal application, and I do not want this is an internal application which is to be BNY, and it's going to be deployed, but I do not want any external request to be served. In that case, I can go ahead and configure in gateways like, okay, allow this subnet virtual network, this allow this thing, and like reject all of the other connections. So that can be done very easily. Now with the load balancing, so in load balancing also you have to be very clear about one part is like load balancing. If you do or auto scaling, then it's going to allocate more resources like servers, for example web servers that you have configured, then it's going to assign like more resources in there. For example, right, um, okay, there is one application that we created which requires replication because for 737 max 737, so we were training AI related like it's several years back. So now the pilot and co-pilot, the pilot and co-pilot, they have to be trained on an AI base. Like how we can train, like they will be conducted test based upon like they'll be given random scenarios, and how the pilot and co-pilot acts. For example, there is a fuel leakage, what are they going to how they are going to solve it and come out of it. So the random problems will be given in a simulation mode. All right. So this is an application that we developed. Okay, it's like several years before in for Boeing. And now the problem is this has to be available. This application has to be available all the time. Now we started creating a replica of database. Like, so the load balance is not just, it can be served from client to server, from web server, from client to the web server. There can be load balancers, and at the same time, from web servers to database, there can be load balancers. You can deploy multiple load balancers in all level, and also you can have multiple cache. Cache also can be like in the entire architecture, you can have multiple load balancers on different levels. For example, if there is a microservice which is running within one microservice and another microservice, you can have load balancer actually. And then from database, you can have load balancer. So now we are particularly interested in solving the database problem because MongoDB, we selected MongoDB, and there is a primary MongoDB was there. There were like secondary MongoDBs were there. So the formula is like the minimum three. It has to have minimum 3 servers running. It has to have minimum 3 servers, and more you can like go like 5, 7 more like that. First is like first it sends the load balancer sends. It detects heartbeats from all the servers. It sends heartbeats like, are you available? Yes, I'm available. Yes, are you available? Yes, I'm available. So it sends back and forth heartbeats. It senses the heartbeats. Now when the primary goes down, it elects a new primary. It elects a new primary because all the requests are served by from primary. Now the database like gets synced, like within few seconds it gets synced from primary to secondary, secondary to primary. It gets synced like very quickly. Okay, and then what happens is, let's see. Mm, Now one of the primary database went down, right? Like had problem, went down. Now the it's unable to load balance is unable to detect heartbeat from here. You know what it does? It it elects a new primary. Say like, okay, secondary one, you are the now new primary. Okay, I'm going to like send you the requests to you. Now you handle it. Now the updations is going to be synced to the secondary. Now it's again going to fail, then the entire application is going to be stopped. So what we decided is to have 5 servers. 5 servers. In that case, one primary goes down, we have 4 secondaries where one of them can be primary. So this is like real world use case that we solved for load balancing thing. The basic idea is like the it cannot go down. Like this is an application, it cannot go down because it's going to be served for pilot and co-pilot simulation for a training purpose, and we do not want to go down. In that case, like how can we employ? Do we need a relational database for this? We don't need, there is no ACID properties or anything like that. So which we like, it's not like transaction or anything like how the pilot is and the co-pilot is going to use the model, and then how they are navigating to solve the problem. All these data is like unstructured data, so we stored in Mongo database, but the problem is like making it highly available because each time like the request count spikes, and then poof, one of the server is like, okay, I'm not going to serve the request anymore. And then now first we had like, okay, single server, then we were like, okay, we have to have at least 3 servers. Then it was like, okay, we expanded to 5 servers then. So this was easily possible because we were in cloud. I was like, okay, so can we provision? Okay, let's provision um let's provision one more data center. And then you might be asking, what does provision mean? What do you say provision mean? So provisioning is something like, for example, you create a Linux server. How do you procure a Linux server? Is like you place a order and then they give it to you, and then you say like, this is the RAM, this is the ROM, this is going to be my overall hard disk memory, and this is what my processor is going to be. But now in the cloud, you can say everything. Like you can say everything, what are the configurations that you need. When you click submit button, it's going to generate in few seconds. But the problem with this approach is like, uh, in an enterprise, you give the cloud application to everybody, right? Like in an enterprise, and then people would be like, they'll select random they'll select random things, like, okay, I think I need only 3 GB RAM. And then when they create, it's going to be a virtual machine with 3 GB RAM. uh, for an enterprise level, we cannot have that, like random developers, uh, like controls the random developers, or like random people, like controls like what's the size of the data server is going to be. So how we ensure that they don't create like this, like, okay, go ahead and use this template. You want a Linux server, use this template. Generally, this is the recommended configurations that you need. This is how, like, you can increase it, like as and when it increases, yes, you can do it, but this is how it's going to be. Now, when I wanted like 5 machines, how it's going to be, we created like pipelines. We created pipelines which we can like which can be for example, a single pipe triggering a single pipeline would create like 5 machines, allocate the resources, and also connect in the subnetwork, and then place. Everything will be done in a single pipeline. You do not need any manual intervention. You just say how many, and then it's going to create everything for you. But what's the advantage in there? Now you can control the configurations that, like, okay, random developers, they cannot decide like how's the configuration is going to be, because you have a fixed template over there. Okay, so why I am saying all these things, right? because because you'll be developing applications thinking, okay, so me and my friend is going to use, not like that, right? Then you say, think like, okay, my entire class is going to use. No, entire TC is going to use. What, and like all the colleges are going to use. What if all over the university, like all the universities in the world is going to use? Think about that. Like, you have to, your you just don't think like, oh, I got a beautiful idea, I got a beautiful idea, okay, let me go ahead and implement it. In that, like, so for example, you come out of TC and then you decide like, okay, I have an idea, something like Mark Zuckerberg, right? Like, he created the Facebook. Something like, you had a bigger idea, okay, and you wanted to create a own or own your own startup, and it's going to be like, how you can create a scalable system. What are the challenges that you're going to face when somebody is like, on overnight your application will be used by 1 million users? Okay, you create an application, deploy it in App Store, and next day it's going to be a hit because it becomes very popular, and then 1 million users are using it. How are you going to handle it? Like, can you think at that level? Because if you're thinking at that level, it's going to help you when you enter an like bigger enterprises, bigger companies like that. That, like, you can ask bigger questions like, how do you decide your architecture? Is it on-prem or cloud? Why do you think it has to be in on-prem? What is the cost of it? Like, what is the load balancer that you are going to have? What is the algorithm that you are using? Why the load balancer is between uh, only between a client and the web server? Why it cannot be like a load balancer can be placed between the application, to the database? Like, you can ask all those questions. Very interesting, I would say. So I worked as a solution architect for I'm working as a solution architect for 5 to 7 years, and it's like each problem that we get is mind blowing. And the enterprise architects that I worked with, they're like great minds. They love problems like this. They'll think about the future and then they design problems. So it's very interesting thing. That's what I'm saying. When you get into it, all you need is a problem. So when you got a problems, like, how well we can solve it, what's the best approach, how well we can expand it, okay, how well we can increase the problem, then think bigger. It'll be amazing. Okay, let's see. Caching, how it improves performance. It reduces database queries and it speeds up responses, and it stores frequently accessed data in memory. Okay, I'll tell you some real time thing for caching, right? Okay. So we created a replication. We created a failover mechanism. Like if there is a failover, if there is an earthquake in there, like how quickly, like all the servers can be like switched to a new. Like for example, you decided your data center is going to be in Chennai, and then but then you also created a backup in Madurai. Okay, in Chennai there is flood and everything is like, all the hardware that you lost. Then how it's going to like pick, your application is going to pick the second data center which is in Madurai and start serving the requests, right? In that case, so this is one of the application that we developed, and the problem with this is like, uh, each time it, like you hit a request, it's going to spill around for like 2-3 minutes. And if you see in real time, any applications that you develop, it has to solve within less than 4 seconds. Be it like thousands of data, be it like millions of data, it doesn't matter. It has to give the answers in less than 4 seconds. Why less than 4 seconds? Because the user is going to feel the difference. Is like, oh, this thing loads forever. We are not patient, right? You go to Google and then you search for it, and then it's like 1 minute it's loading. It's like, what's happening? Because humans should not feel the lag in the system. So anything that's like less than 4 seconds, you are going to feel the lag, right? So uh, it was taking 2 minutes, and business users were like complaining, like this thing takes forever. Now what we did is like, okay, let's see, what are the frequent queries that comes in. Can we cache the results in there? Okay, what is the amount of caching that can it be 10,000 or a million? Because each time, if it does not like, if it's not in the top results, then it's, again it has to remove the cache and then freshly load the data and show it. It's going to take a lot more time actually, right, than the previous time. So your caching mechanism is also very important. Okay, what are the different types of caching? Client-side caching, which is storing data in a user's browser, and server-side caching, which is using in memory databases like Redis and Memcached, and CDN caching. This is distributing static content closer to users for faster access. Which does CDN caching? The one thing, Netflix. Like, you see, why do you think CDN caching Netflix does? I hope like most of you at least like watched movies in Netflix, right? You see in Tamil Nadu, we watch a certain kind of films. All over India, we watch a certain kind of films. But it's not, same thing is not applicable to people in US or different countries, it's like maybe Singapore or like Korea. But then, but each time the user clicks on like, okay, play this movie, and then immediately this data starts loading, and then how do you think it does is, first it tries to understand, like the CDN, like caching servers are employed, like there are like CDN data centers are available there here, and then it caches data based on how users, how first it creates, the algorithm finds out like, okay, this particular user is interested in this region user is interested in this. Okay, let me load all these things in a particular thing, maybe whenever the user clicks on it, so that I can immediately serve. I don't have to go to the place where the actual movie is stored, right? So in that case, it goes and gets the it doesn't have to go and like fetches the data from the database and then load and then play it for you, when it like can be served immediately in the caching server. Like Netflix has huge caching servers, and it's amazing. and each time these thing like gets updated automatically as and when the users taste changes, then it unloads and loads the caches. So this is a great example. And another thing is like server side caching for, yeah, this we discussed about it, like server side caching. uh you can do it like you can create it like, but you have to apply your own judgment, and also you'll be working with business owners as well. Like, what do you think, what do you think the load can be, how much can I stretch? Because anything which is lesser is going to create a lot of load in the server. Anything more is going to create a lot of load in the server. Anything less, user is going to feel the lag more. How can I solve this? You'll be working with business users to understand it. Something like CDN caching, for example, now for for clinical database, when you are deploying, then you'll be like, okay, which branches can I set up one here? Can I set up one there? So you'll be deciding on that. Okay, choosing the right database. Obviously, for anything related to transactions, you will be choosing this SQL only because it has ACID properties and it's also usable for transactional systems, and it's structured. And NoSQL database is like flexible schema, and it's scalable, and it's used for large scale applications. So the one thing that like I have done is like the hybrid ones. You know, the beauty of hybrid systems, like even for NoSQL database, like, okay, I am going to use an unstructured data everywhere, but how can I use the SQL there? Maybe I can use the index related information in there. Maybe like few information that can be taken for, which can be used for NoSQL, can be used in the SQL database, maybe in the lesser configurations, but like we can use hybrid also as well. So we have like several kind of database for NoSQL, right? Like something like MongoDB, GraphQLDB, so many good databases there, and each is applied for their own applications. Actually, for example, for different applications, you can use, right, like which now NoSQL database that you can pick. Next is, what are the techniques used for optimizations? Indexing you do all the time because it speeds up the search queries. Indexing will be doing. Sorry. And sharding is like splitting the larger database into smaller and manageable parts. So you create different shards. For example, imagine you order a pizza, right? You order a pizza, and then your elder brother comes and it's like, I want two pieces, like bigger pieces. And then your younger sister comes like, I want little. Okay, I don't want it. So now you think in terms of like, not everything is going to take the same amount of thing, right? Like, now how can I split it and then go and check in each charts? Because in that case it'll be very efficient, because how can I go check in each sharding? So this retrieving is also faster, and retrieving is also very faster at the same time. The manageable, it's very manageable actually. Replication. Replication is like creating multiple copies to enhance availability and performance. I wouldn't say availability much. Um, there is a theorem like CAP theorem, um, which states that you can test this. Okay, if you can make your system 100% available, and you cannot make it like 100% fault tolerant, in the sense like, when do you want to replicate? You wanted to have multiple copies. I do not want to lose my data. Okay, create a data center here, have all my database here, and means my So there are like in replication there are multiple cases are there. There's a case like live application. There is something like active passive application, passive application, something like that. So what do you call it as live is, okay, I am going to have a web server, I am going to have my database server, I am going to have whatever you are deciding as part of your architecture, right? A, B, C, Z up to Z, and whatever exact configurations have to be present in data center 2 as well. In the sense, for example, I say like my data center 1 is in Chennai and the other data center is in Madurai, right? I wouldn't like even Madurai. So let's go further away, right? Like maybe Kashmir or Pakistan or Bangladesh, something like that. I'm going to keep the data centers like, but when I what does live application means? When the moment your application goes down, the live application, it will take the data center 2 and then start running, and it will have the exact amount of data in there. Everything will be synced up immediately, and then the exact configuration, everything has to match. All the data, whatever is present in data center 1 has to be present in data center 2. How do you certify the application? Now you claim like, oh yeah, my application is live application. Generally government comes and asks you this when you're running a critical application, right? Like Bank of New York actually takes care of trading for US system actually. There is something like broker dealer clearance. If it goes for like few minutes done, it's going to be several $billion. So billions of dollars will lose actually. So something like very critical application generally is taken care by Bank of New York only. It's done by Bank of New York, but it's not just for Bank of New York. It's for all the banks, for all the US economy. This project is done by Bank of New York. So I was part of the project like sometime before. Now the government will come and ask the application like, okay, did you guys, you claim that you're a live application, right? Can you certify that for me? How do you certify in a real time? Will you be like pulling the plugs off like, okay, data center go down and then like test the other application? No, you'll be simulating it. You'll be simulating in it before going for testing. Sometimes like how many times it has gone down, all those data has to be like calculated in metrics, and then it has to be available for the government to verify actually, because it's a critical application. You cannot say like, okay, this is my active application, this is like active passive application. Active passive application is something like, oh, you don't have to like keep all the servers exactly matching. You can be like, this part of the application can, it's not like 100% available, but it will be downtime for like 2-3 hours is fine, 1 hour is fine, maybe 5 minutes is fine. You say your downtime application like how long can it be downtime, like 99.99999 percentage, or like 99.9 is very less actually. If you see for availability, 99.9 percentage is very less for a highly um, critical applications like that. So when you create replication, tell me like, if you are saying, if you are claiming that your application is 100% available, then you have to absolutely compromise on what the data that you are serving. For example, Google or Gmail can be 100% like Google can be 100% available, right? The reason being, it need not serve all the pages in the top one. Anyhow, you'll be searching. Sorry. Lakshmanan accepted. Sorry about that. Getting calls. Oh shoot. Second. No, it's not stopping. One second. It's my husband. Okay, so now you cannot be like your data cannot be 100% sure. Your data cannot be 100% sure because you say like, okay, the user is searching for keyword ABC, keyword whatever, like uh, ABC, but you don't have to retrieve all the results in the first 10 like results, right? It can be at the last results, maybe it's missing. Nobody's going to ask like, oh, that content is particularly there in that website, but why you haven't loaded for me? I searched for all the pages, but it's not there. Nobody's going to ask. In that case, availability, generally the availability is higher, so they don't worry about like the accuracy of the data. But for certain applications, something like banking applications, you do not care if it's like, okay, if it's not going to be available for 1 minute, 2 minutes, but you wanted the amount to be exactly deducted, like the transaction has to be in the exact number, right? Like just to make sure it is available up and running, we cannot deduct like more $100 more, and then, oh yeah, because the server is down for some time, maybe the calculation got, it did not update. Maybe we deducted the money, but we did not update in your account. Maybe because the server is down. Oh, we can never say that, right? So what cap theorem suggests is you cannot make like consistency, availability, or partitioning all can be done at the same time. If you have to pick any two of them, you can implement it. um uh, okay, you can skip consistency, you can make availability and partitioning available at the same time. You can make like a consistent consistency and partitioning available, but you have to compromise in availability. The idea is like you have to understand what kind of application that you're working on. Can it compromise on consistency? Can it compromise on availability? Can it compromise on partitioning? So which one it can compromise? Like which one it can compromise? The other two you can pick and then make sure like it's built thoroughly. In that case, for our case, for CDN, the consistency is more important than availability, right? Consistency is very very important. So in that case, like, yeah, availability can be little here and there compromised, but like consistency has to be very, very much available. So that's the reason I was like explaining this a bit more. And the conclusion is like, yeah, CNNs have revolutionized medical imaging by improving diagnostic accuracy, and advanced architectures like ResNet, DenseNet, EfficientNet, and VATs further enhance performances. And the challenges in data availability, interpretability, and regulation must be addressed. If you cannot address the regulation, you have to like adhere to whatever the regulation in the countries that you are going to work. For example, you might be working for UK related, you have to adhere to the rules. And because if you bypass the rules, it's going to be it's going to backfire on you. So yeah, you have to adhere to regulations. And the future lies in AI driven hybrid models, and it's going to optimize efficiency and trust. Yeah. So as and when like we get more larger data, right? Like most larger data, when we train the models perfectly, it's going to increase our efficiency. And it's on time. And let me stop sharing. Yes.
Ma'am, the participants will post the queries in the chat box.
Mm-hmm.
Just read them to you. Actually, I guess they are typing, ma'am. I'm still not getting.
Oh yeah, so I'm trying to read. PNY in clinical for the matter CNN deep learning. Oh, there were like multiple questions possible. Okay. We consider for the matter CNN deep learning techniques and able to migrate from Oh, for the credit card, some user is asking like, oh, it's playing with credit. I was just saying for fun, like playing for credit card, playing with credit card. I did not say like I'm just like to make sure it's very serious. I just said it for fun. Like, if you enter the credit card, it's going to cost you a lot of money. Yeah. Hmm. Uh, So like we can use like Menis dataset for handwritten digits, and we can like compile models and then we can train models, and also we can make predictions. This is for the multi-class classification, right? Um, so first you would be like you'll be like importing something like TensorFlow and Keras and layers, something like that, and then you will be processing data. Uh, you'll be processing data using like reshaping or and then you'll be building CNN models. For example, max pooling and then dense techniques, and then you'll be compiling and then training and then use predictions actually. That's how you will be using it for multi-class classification. Clinical data set augmentation. Oh yeah, so we do this for AI, like you'll be like creating synthetic data generation actually. For example, you sometimes you cannot predict then like how we can simulate data based upon it. Like you can generate using synthetic data generation, and then there is a augmentation imbalanced data sets you can do, and you can do some data masking, like you can do like randomly like uh, mask certain data values to increase the robustness. Oh yeah, and we are done here, 9 p.m. Sasi? Okay, so somebody asked like you can contact, I'm not in social media. You can contact me in Nagalakshmi Chidambaranathan in LinkedIn. And then more questions you have, you can post it there. On any help that you guys need, please reach out to me. I can help in whatever way possible. Nagalakshmi Chidambaranathan in LinkedIn. So I'm not in social media. So use LinkedIn for professional communications. Thank you guys.
Ma'am, we have one more question. Is it fine if I read it or I shall send it to you?
Yeah, just one question. Yeah.
Depending on the level of features, that is low level, mid level, or high level, do we have to go for advanced CNN model like LENet, BGGNet, and so on, or we can just increase the number of layers with basic CNN model?
No, if it's level of like features are getting increased, you have to go for the advanced ones. See, it's also on the budget. Okay, so you'll be working with on a budgeted system. Like what's the infrastructure cost your organization can afford, or like how long it's going to afford. That also plays a major role, because once you come out of college, and then like when you'll be working, generally they'll have like, okay, per year for infrastructure I can handle this much amount of money. Are you going to reduce work by spending more money? Business doesn't want it. Like we are fine, we can do with our own hands. Like, so can you increase, like, can, like, okay, you're going to spend $1 million on like development, or like you're going to have $100,000 on infrastructure. What is the value that you are going to add in? So what is the savings that you are going to create? If it's going to be more, go for the higher ones. You don't have to build on the basic CNN. So it's the money also comes into picture. It's when you're working with business users, and you'll be deciding based upon the money factor as well. Okay, we will wrap it up.
Yeah, okay, ma'am.
Thank
Thank
you.
you, ma'am. Thank you for sharing your expertise on advanced CNN architectures and the clinical applications. And ma'am, your insights into deep learning innovations and AI-driven automation have provided us with new perspectives on AI role in real-world healthcare solutions. Thank you, ma'am.
Thank you. Thank you. Thank you, guys. Bye.
So participants, that concludes day 5 of our FTP. Today's sessions deepened our understanding of optimization strategies for deep learning and AI model architectures tailored for clinical datasets. We explored how fine-tuning deep networks and leveraging advanced CNN frameworks enhance the efficiency and accuracy of the AI-driven healthcare applications. So participants, just to remind you, assessment test will be conducted at the end of the program. Minimum 80% of attendance and 70% of marks in the test are required to obtain the certificate. As we will also be sharing the proof session recording in YouTube for monitoring the attendance, we request you to maintain minimum of 80% of attendance. And kindly provide your valuable feedback by either scanning the QR code or using the link shared in the chat. Your feedback is very important to us, and attendance will also be monitored based on the responses received. So thank you, participants. After sharing the feedback, you all can, and we look forward to the final day of our sessions tomorrow, where we will wrap up this journey of the FTP and have a wonderful evening.